if you're seeing this, it probably means that you're catching this very early. Um, since I've streamed it, since I started streaming it, and I haven't like removed the beginning part. Maybe I've added chapters so you can skip to it, but or it means that I just forgot or thought about it but couldn't be asked to do it. But you can skip ahead. Today we're going to continue with this Erlang series. Um, Erlang is a programming language made in 1986 by Ericsson, a phone company, mobile phone company, I think, in Sweden. And it was to run their system, their online system. So it's all about like parallel programming, reliability, that kind of stuff. WhatsApp and Discord has used the same virtual machine, the VM that runs Erlang called Beam. I don't know if there's like three kind of big languages on top of Beam: Erlang, Gleam, and Elixir. And I don't know which ones they used. We've gone through quite a bit of this book. We're like going through Learn Use Some Erlang for Great Good, similar to Learn Use Some Haskell for Great Good, in the same kind of style. It seems very long. So we've gone over the intro, how to run REPL, what the various basic data types are, how to work with modules, um, and some guards. Because it's a dynamically typed language, guards are very important. They kind of make sure that what you think your function is getting actually is the stuff you want and not some other data type or shape even. Um, some more guards, and then we're in recursion. So here we are now. We're still pretty early. Oh, I'm not showing my screen. So we're still kind of early in the book over here. We still have quite a bit to do. Wow. I'm not sure that I'm going to get through all of it. I want to keep going until I feel like I can say I know basic Erlang and I could make stuff with it. Not sure what I want to build yet. We'll see. So, how's my day been going? It's been going all right. I woke up early, so I kind of had an early start. I got like my laundry done, all that kind of stuff, so that was nice. Um, I have my routine of like stretching and things like that. So yeah, now I just have I want to stream a bit. I also want to work during the stream a bit. So I'll do that in the second half. Um yeah, yesterday I had a big accident sort of thing because I went out and I was in this area in Paris, this train station called Châtelet, and it's like known for pickpockets. And I swore like I had my wallet out from my purse, and then next second it's gone. I'm like, I fucking got pickpocketed. Oh my god, I lost my wallet. So I'm freaking out, and I call all the credit cards and cancel them so they don't work anymore. But then a couple hours later, the person that I'm with is I'm going through my backpack because I had some stuff there, and my wallet comes out. I'm like, I have no recollection putting it. I never put my wallet there. What the fuck? How did it get there? So now I have no way. to pay for stuff because I canceled all my cards. And I didn't even need to, so it's like self inflicted pain. Isn't that terrible? Also, I've been kind of entertained by this whole rapture thing on TikTok or wherever, right? All these people thinking that it's the rapture now this week. And I just like keep imagining what they're doing, like hanging out at home or being ready, beam me up, but like nothing's happening. I wonder if each day they wake up thinking, oh shit, maybe like how would you even know? What would you do? I guess the assumption is if the rapture happens that like people think you'll notice like there'll be a lot of people missing, right? But what if like nobody's actually meets the criteria for rapture? You would never know. I did a post where I was like, the rapture already happened, but none of us were good enough. You know, we just have no idea. It could have happened 100 times, and we would have had no idea. I guess they look at their friends that they consider like unimpeachable in some way, and like they're like, oh well, if they're still here, then it's not the rapture. What else is really funny is like I was looking at the YouTube stats. The shorts that I do, it's like 70% women audiences. And the long videos that are mostly because in the shorts I talk about random stuff. But in the long videos, it's all men. You're men. If you're watching this, you're a man. If you're a woman, I want you in the comments. Tell me because YouTube is telling me there it's literally 100.0. It's not like zero point 0.3 or whatever. It's like there are zero women watching this stream. What? Like what's wrong with Erlang, gals? Like it's a nice programming language. Get into it. Also the stuff I'm doing for work is a little bit different now. I think it's going to be a little bit more interesting to stream too because it's a little bit more approachable. So we'll see how that goes. God, it's so hard to get started. If you guys ever think about streaming or when I start when just said it's hard to get started, I was thinking of my day, just like it's so hard to get started for my day. This is like the first thing that's like productive. I guess you can say laundry is kind of productive, but not really. It's just like something you got to do, right? So, but yeah, when streaming comes, you just hit the button and you go. And I've had a lot of people tell me like they want to stream but they don't like it or they're scared of it or whatever. It's like just hit the button and go. Just do it. No one watches, no one watches. I think it still helps me keep focused and I want to learn Erlang anyway. What I really want to do is like actually after I learn something, actually maybe redo it as a tutorial because it's a very different format. Come learn with me or, study with me sort of thing versus I'm gonna help you understand it. The only thing is I really like learning and I'm still trying to figure out if I like teaching. I don't know if I like teaching. I like doing talks, but they're not like teaching talks. They're like about an experience. It's like a story. So maybe there's a way for me to make it like a story, then it could be more interesting to do. Also, it's finally gotten cooler here. I hate the heat, so that's a real benefit for me. All right, let's kick some ass and get started. I'm not gonna do my usual review because what did we learn last time? We learned how to do recursion, but we kind of know recursion already. What was the thing before that? Yeah, some guards. So yeah, I'm not gonna do that. We're just gonna go straight in and do quick sort in Erlang. Actually, false start. There was another thing I want to talk about. Um, I've been thinking about like people trying to like AI. Excuse me, AI and the role it's gonna have for new developers coming in. It feels like a lot of companies are hiring like medium, you don't say medium, intermediate to like expert programmers, but like very few junior programmers is kind of hard to find, maybe as an internship. Um, so like what's the future of that? Because AI can do so much of the hi there, Hissim's vault. Hi Sims, Hissims, tell me how to say it. And I was wondering like f- how it can be made easier for more junior people to get in and also like advance now that like there's AI. And I'd want to like maybe create a talk around that or a blog post. Something else I want to think about because I've always had an easy time sort of with people skills at work, and that's helped me in my career. And I notice a lot of people, especially developers, don't have really good instincts or intuition for people skills. And a lot of developers have this idea of I'll just like work hard and I'll go. I said his sims, but like what you wrote, I would say, hey Sam. Is it hey Sam or is it his sim? Um, okay. So what was I saying? Um, yeah, I've always had pretty decent people skills, and a lot of developers don't realize how much that counts because they think they're just going to do good work, they'll get recognized. But it's really not just meritocracy. It's really like, I think there's some stat that like agreeable people or people that the company likes, they're much more willing to keep around and they'll fire the people who don't really like fit in or that aren't easy to work with even if they're great. There's always exceptions, but um and I'm certainly not saying be a brown noser to always agree and say yes to everything. I guess I think that there's just a way of managing perception and also managing how you work so that you can be noticed and be seen as an asset and valuable. Um, Something I was saying to someone before was how if the company is telling you to do something, often it's not the thing that they actually need the most. The thing that they need the most, they're actually afraid to talk about because they don't know. Maybe it's a vulnerability, a weakness. Maybe they don't think anyone can actually do it. So I've always found that at work, I've had to like listen to like the higher ups, like what it is that they're not saying or what they're really, you're trying to figure out what they're afraid of and then work on that. So maybe maybe it's a scaling problem that they're afraid of, or they don't think that they can ever build anything that will like be stable enough in a certain area. Whatever it is, like find it and like show that that happens, that you can do it. Anyway, I have a lot that I could talk about there. So just something that was on my mind. All right, now for real, we're going to do we're doing Erlang here. We are on the um learn some Erlang, learn use some Erlang for great good. We are on the recursion chapter, and we stopped midway right at Quicksort. So look at the other videos if you want. It's ha instead of hey, so it's hasim. I hate you so much. I learned something today. Um, all right, what was going on? Right, so look at the other videos in the playlist if you want to learn Erlang. It's been fun. I hope I get to use it someday or want to use it someday. Let's see here. Quicksort. Um, I can and will now assume recursion and tail recursion makes sense to you, but just to make sure, I'm going to push for a more complex example. Quicksort. Yes, the traditional, hey, look, I can write short functional code. Canonical example. A naive implementation of Quicksort works by taking the first element of the list, the pivot, and putting all the elements smaller or equal to the pivot in a new list, and all those larger in another list. We then take each of these lists and do the same thing on them until each list gets smaller and smaller. This goes on until you have nothing but an empty list to sort, which will be our base case. This implementation is said to be naive because smarter versions of Quicksort will try to pick optimal pivots to be faster. We don't really care about that for our example, though. Okay, so we can kind of look at this for a sec here. Um, Looks like they've picked the pivot, they got the rest of it, then they break it up into a smaller and larger part, and then they quicksort that. So let's get rid of that and let's try to write it ourselves. So first thing first, we're going to make a new file. Whoops. We're going to call this quick.erl. And if we remember the module syntax, I think it's something like module quick, and this quick has to match the thing earlier. And let's just make sure that that actually makes sense there. I made a recursion.erl. Yeah, that's how it looks. And now we're going to add a function called quicksort, I guess. Or maybe we just call it sort because it's already like, it's already under the module quick. And we're going to sort a list, right? So if the list is empty, then we return the list and we're done. Otherwise, it's not empty. So we're going to pick, we have the head and the tail, but we said we're going to pick the pivot point by using the head. So just to go into Quicksort a little bit, it's not like I write these very often, but the idea here is that you pick an element, not like a position. You're not, I remember I was getting stuck earlier on, like I kept thinking you're pivoting, so it must be a position. It's not a position. You pick a value. That's one of the elements in this list. So if it's like 1, 2, 3, 4, your pivot might be any of those elements. It can't be 5, it can't be 0, it has to be 1, 2, 3, 4. So you pick something like we can pick 1, and then we make a list. We break up the rest of it, either being smaller than that element or larger than that element. And then, so then we'll have basically three parts, right? We have the smaller side, we have the actual pivot values. There might be more than one because I guess they might be identical. Like it could be 1, 2, 2, 3, or 1, 1, 2, 3, 4, whatever. And then you have everything bigger. Um, the smaller and bigger ones aren't sorted, so we have to call sort on that too. Quick sort on that too. And it's going to do the same thing. So it's recursive because now it's a smaller list, right? It's smaller, at least by one, because you've pulled out your pivot element, and you keep doing it until it becomes empty, and then you return um, the empty list. Same, you could have made it also, if it has one element, no need to do that either. All right, so let's see. We got our pivot. We'll call it P. And this is how you deconstruct. This is how you pattern match a list. And then we'll call this one rest. We'll call it R, right? PR. And in PR, we're going to call, we're going to have a helper function called partition that takes in the pivot point. It'll take in the rest, and it'll take in everything that's smaller and everything that's bigger. And smaller and bigger, this is what it's going to recursively call on itself. So we don't need to, we pass empty list here. And then it's going to return us small, smaller, bigger. All right, so now we have that. And then I think we do semicolon because semicolon means or else, right? So now we can have another line. And then we call sort. So now we call, the answer to this is a list that is the, well, look, first we can think of it like this. Smaller, let's say smaller is a list, plus the pivot, plus bigger. And that's the return value, right? But this is actually not sorted. So we have to call sort smaller, and P, this isn't a list, so we need to make it a list, and sort bigger. We need to make it a list because concatenation only works on lists. I think that's right. And now we have to write partition. And it takes the pivot. It takes the rest. Wait, what did I do with rest? I'm not using rest, am I? Oh yeah, partition rest. Yeah, that looks right. And then smaller, bigger. So if rest is empty, we have no more to process, right? Then we just return smaller, comma, bigger because we've constructed it. That's the idea. Otherwise, we're going to take, we have heads, right? We can break this up too. We'll call this tail. Smaller, bigger. So now we have we can use an if statement or a case statement. I'm trying to remember the syntax of it. I think we have it in uGreet. Let's see. Do we have case in here? Yeah, case. Oh, we have an if. Where's our if example? Here we go. So we do if um if is h is less than p, right? Like basically it's smaller than p. Then let's make it less than or equal to, and that way we can just put it in smaller. Then we're going to return it's smaller, so it should be added to smaller, right? Smaller plus, we can actually, I think it's more efficient to put it like this. So that's our new smaller. And then our bigger doesn't change. Biffer. Biffer. Bigger. Um, and now we can say if h, it's really a true, right? Because the other option has to be that it's bigger. So then we do smaller, comma, p bigger. I think we need a semicolon here. And then we have an end here. Let me see. Format. Formatter is not available. Why? Partition. Partition. Why is my formatter not available? Probably because I don't have let me see. hx minus minus health Erlang. I need Erlang ls. I guess I never set it up. I have it under my shell, right? Yeah, I have no. Oh, I have this. Yeah. Let me add this to my main Nix config. Hello? I am out of it. There we go. Okay. And I wanted to add, where's our Erlang? Oh, but I have this here. I just wrote it wrong. I guess. Let's try it. Let's hope this works. When Nix works, it's great. I wonder why it's rebuilding so much stuff. Anyway, there. Now we have Erlang ls. So now I should be able to load my quick and just do format, and there we go. Sort of. What the fuck just happened? Parameter 4 is unused. Yeah, that's a problem. Um, Certainly my brain's not working. We need to, this is recursive, so if it's not empty, then I've moved one, but I'm still not done. So I have to call partition with the same pivot with rest now. So it's just tail, and then here's smaller and here's bigger, right? That makes sense. And here I call partition with the same pivot, tail, but now this is different. There we go. And why doesn't this format? What happened to my Erlang stuff? Why are you so fucking confused? You were working before. Syntax error, right, because this looks like this. And then I do this. No. Syntax error plus plus. Something look wrong here? Looks right to me. Maybe it's that it's a comma? Oh, maybe it's a comma. Which means maybe this is a comma also. There we go. That looks better. Why doesn't it like true? Syntax error before this. No, I think this one is a semicolon. Comma between statements in a function, semicolon, and then we have to do export. How does this look? We type in export, the name of the function, partition, and partition takes in 4 parameters. It's our biggest function yet. All right. Ah, so at the end of each of these function clauses, we put in semicolon. There we go. That's better. Partition 3 undefined. 1, 2. Oh, these are supposed to be separate. A list that is bigger and smaller. There we go. And here, smaller and bigger. We just get rid of that. And now it looks happy. So let's try running this. Let's try running. Oh, this isn't happy here. He's not used because it's not. Yeah, let's just put underscore there because we're not using this variable. We have nothing left to do since we've gone through the whole list. All right, let's try running this. So to compile this, we do quick. And now I should be able to do quick colon. So let's try partition first, right? Partition takes a pivot. So let's pivot on 3. and give it 1, 2, 3, 7, 10. That's kind of, well, we'll do it. This is already sorted, right? So, oh yeah, we need to give it the bigger, the smaller, and the bigger list. So far, we've nothing. So there it goes. This should have returned smaller and bigger, but I've obviously screwed up. Ah, I'm adding the pivot. I need to add the head. We compared the head. There we go. Compile quick. And then we run quick.partition 3, 1, 3, 7, 10. I'm still not used to this French keyboard after so many years. Where's the dot? There it is. It's supposed to be semicolon. All right, 3, 1, 5, 10. I'm putting it in the wrong place. I'm putting it in the front. It should be probably in the back or something. Let's see. If H is smaller than P, then we have to like, oh no, that's right. It's partition. That's right. This isn't sorting. This is just partitioning. Let me run the stuff here so that we don't have to keep recompiling. Well, we have to recompile, but I don't have to quit out. Quick partition. So we give it the thing. Let's do 5 this time, and we're gonna give it a bunch of numbers. We gotta pick a 5. There we go. I always put dot here. Okay, so this is going to be smaller than or less than or equal to 5. So we have that. And then we have greater than, right? That looks correct. So now we can test out sort and see if that works. Sort just takes in the list. And it has 1, 2, 3, 5, 8, 10, 11, 20. It's not length. There we go. So there's 8 elements in the sorted one, and in here, I assume it's 8 also. Yep. All right, so we wrote Quicksort. I think they wanted a better version. They have a version. So this is similar. Let's bring up ours. Compare. Yep. Same pivot, rest, smaller, bigger, just naming stuff. Yep. Exactly the same. Partition. Yep. I see. They don't call, they don't do true. They do H greater than. I think they like this because it makes it obviously exhaustive. Oh, now it formats. There we go. It just needed to actually be syntax free for it to format correctly. And then we can use list comprehensions here. I guess LC for list comprehensions instead of making a partition function. We can try to do that. Here, I'll get rid of this code so you don't see it. Is everything making sense to everyone so far? Probably. I'm tired. All right. Right, we're gonna do list comprehensions. So let's see here. We basically want to get rid of this code. And we just want to put in the list comprehension here. So let's do it like this. Let's do smaller is equal to the list comprehension we're getting the elements from R here, right? Where n is less than or equal to R, and this was comma, right? I think so, yeah. And greater or bigger, they called it. No, we called it bigger. They called it larger. N is greater than R. Now we get rid of partition. Does that look right? Why does it say it doesn't know N? Oh, right. N is coming in from R. I am really screwing this up. There we go. So N is all the values from R, which is the rest of our list. And then we sort those and we put our pivot right in the middle. You know, we could like pick all the ones that are equal to pivot and put it in here, right? But we're just doing it one at a time. Okay, let's see if this works. Let's compile. And then we run Quicksort here. There we go. Oh, that did not work. That definitely did not work. What happened? Smaller. N is less than or equal to R. Bigger. Sort smaller plus P. Why does this look right to me? all the numbers from rest that are smaller. Oh, smaller than p. What am I doing? What what does even comparing it to r even mean? All right, let's try this again. There we go. That's so much better, right? Okay, so we have that. Um, and you could take this if you wanted to and put it in here. Oops, why didn't that work? There. And we can do the same thing here. And now we recompile and we run Quicksort. It still gives us the right answer. So it's kind of like a shorter function. Okay, let's skip that Kool-Aid part. We have a picture of a tree, so obviously they're going to make trees. That kind of like makes me nervous. I never liked trees. So tired. I'm supposed to be upbeat for you guys, right? But realistically, can't always be upbeat. I mean, the fact that I'm doing this, I gotta pat myself on the back for. I also want to set up my Raspberry Pi 5 and put a mail server on there and all sorts of stuff. It's on my list. All these things on the list. More than lists. Speaking of lists, by reading this chapter, you might be starting to think recursion in Erlang is mainly a thing concerning lists. While lists are a good example of a data structure that can be defined recursively, there's certainly more than that. For the sake of diversity, we'll see how to build binary trees and then read data from them. First of all, it's important to define what a tree is. In our case, it's nodes all the way down. Nodes are tuples that contain a key, a value associated to the key, and then two other nodes. Of these two nodes, we need one that has a smaller and one that has a larger key than the node holding them. That's a little weird. I thought we'd want values, but okay, key. So here's recursion. A tree is a node containing nodes, each of which contain nodes, which in turn also contain nodes. This can't keep going forever. We don't have infinite data to store, so we'll say that our nodes can also contain empty nodes. To represent nodes, tuples are in the appropriate data structure. For our implementation, we can define these tuples as node, key values smaller, larger, a tagged tuple, where smaller and larger can be another similar node or an empty node. We won't actually need a concept more complex than that. Okay, I think. Does this make sense to you guys? I'm not really sure. I mean, I get the concept. There's a key and a value, And there's a smaller, this is a node, right? Smaller and larger. And if you want to have an empty node, you say node nil. I see. A node is an atom because it's lowercase. Okay, this makes sense now. Yeah, it's interesting, right? Like, do you really need this atom? It's just, that's why they call it a tagged tuple, because it's a tuple that has this tag that's an atom, and then this is basically the value of the tuple. Let's start building a module for our very basic tree implementation. The first function, empty 0, returns an empty node. The empty node is the starting point of a new tree, also called the root. Okay, so let's make a new file, and we'll call it module tree, right? Yeah. And we'll export empty. And what does empty take in? Nothing. So it's empty 0. Oh, it doesn't know the name of the file. Tree.earl. Now it can do this. Now we write the function empty. It takes in nothing, and it returns node followed by nil, I think it was. All right, does that look right? Oh, they made it nil in quotes. Why would they do that? Why would they do that? Isn't that weird? Because nil is equal to nil. Well, I can make it more explicit by saying this. Yeah, they're the same. So why would you make it, why would you put quotes under it? That's sort of weird. Maybe we'll learn something? I don't know. Doesn't make any sense to me. Since I don't understand it, I'm not going to do it. I wish this chat wasn't backwards. How do you set the chat so it doesn't go backwards? Let's see. Oh, there's something called compact mode. Oh, maybe we want compact mode. Yeah, we can just leave it like this. But I don't know how to, yeah, they don't have a way to, they don't have a way to sort of like reverse the order. That's sort of weird. I'm sure that's fascinating for you. All right. Let's see. By using that function and then encapsulating all representations of nodes the same way, we hide the implementation of the tree so people don't need to know how it's built. All that information can be contained by the module alone. If you ever decide to change the representation of a node, you can then do it without breaking external code. All right, so it's just saying don't mess with the internals. To add content to a tree, you must first understand how to recursively navigate through it. Let's proceed in the same way we did for every other recursion example by trying to find the base case. Given that the empty tree is an empty node, our base case is thus logically an empty node. So whenever we'll hit an empty node, that's where we can add our new key value. The rest of the time, our code has to go through the tree trying to find an empty node where to put content. Does this make sense to everyone? Your tree basically has two, like, its value. It kind of has three things. It has its value, which is actually a key and value, but we just call it value. And then it has smaller and bigger. So basically left and right, or however you think of it. So it's a binary tree. It can only have two other nodes under it. So obviously you can only add values since a node is a value, you can only add values by adding it to a node that has no children, or at least is missing one child at least, right? Because if it already exists, then you can't you can change its value probably, but you can't add a new node. You have to like add it underneath that node. um yeah, an empty node has no value. So when we start out our tree, it has no values. It's empty. So we have to add nodes under it so that it becomes this node plus, it has smaller and larger. To find an empty node from the root, we must use the fact that the presence of smaller and larger nodes let us navigate by comparing the new key we have to insert into the current node's key. If the key is smaller than the current node's key, we try to find an empty node inside smaller, and if it's larger, inside larger. There is one last case though. What if the new key is equal to the current node's key? We have two options here. Let the program fail or replace the value with the new one. This is the option we'll take here. All right, this looks like ugly code. Insert takes in three parameters: the key, the value, and the node. So if you try to insert a key and a value into a tree that is basically just the empty tree, this is the current node we're at, right? So we might have recursed. If it's empty, then make a node that has key value, and so it goes to the left, right? Key value, and then no, it's just key value and has an empty left and an empty right. That's what it is. Okay, makes sense. So it's kind of just like you have, if you have a node that's nil, then it returns it by just doing key value. And then on the left, it's nil. On the right, it's nil. That's what it's trying to say. Um, the second case is when the tree you have has a key value, and then you're comparing to see if your key is less than or greater. So if it's less than, then we're going to go into this, we're going to recurse. You see this insert call recurse into the left side. We're going to insert it on the left side and leave the larger the same. And we do the opposite here for greater than. And then the last one is when they're the same. So when they're the same, we're just going to end up replacing the old value with our new value. All right, let's try writing this ourselves. Here's just a note to ourselves. Note, node structure is node, the atom, comma, a tuple where we have key value smaller, greater. Right? That's what we have to remember. Empty node is node, comma, nil. All right, so now we're going to write a function called insert. And the first case is we're trying to insert and the node we're looking at is empty. So insert takes in, let me move this out of the way so I'm not tempted to look there. We get in a key, we get in a value, and we get in a node. And I think that's it, right? We get a key, a value, and a node. I think that's it. Now, our case is we think that node is going to be equal to the empty node. So we are matching on this. And what do we return in this case? We return the, since our node is empty, we're going to return node, comma, key, value, and then the two child nodes are empty. That is not the prettiest looking thing. And it's not happy because what? Syntax error. Why syntax error? Why is there a syntax error here? Function is unused, key is unused, value is unused. But what if I just do this? Are you happy now? And I put this here. Insert takes in 1, 2, 3 values. Oh, now it's happy. So there's something wrong. Oh, it's because I put a comma semicolon there. If it's the end, it has to be period. Right, there we go. Okay, perfect. All right, so now, even though we're not done, we should be able to call this function and compile it. Compile tree, and then we do tree colon insert. We give it a key value. So let's do it like the key is age and the value is 19, and we're putting in a tree that is empty. There we go. So it added, I guess we can call it like this, right? That just makes it easier to understand. All right, that was the one case where node is empty. The next case is key is smaller than node's key. So we have a node that actually has a value now, and now we're going to say, oh, we have to go to the smaller side. Oh, Sustrike, I'm new here and just starting out with web development for the past month. Sometimes it feels overwhelming, like there's endless knowledge to learn. Do you have any tips on how to keep that spark alive and enjoy the process of coding? What an amazing question. I don't know if you're still here. This is a great question. And this is something like I've sort of tried to help a lot of junior coders before. And it's something that happens a lot. Like, let me think about this. People want to get to the end. They want the result, right? And so maybe it's just like getting a job, programming or whatever, it's for the money. If you're doing it 100% just for the money, there's better professions to get into, right? Just do something else. But if you actually enjoy it, then make sure that you can do it for fun. It's really that simple. Like what I'm doing right now, I'm not being paid for this. I'm not going to get my money back for what I'm doing right now, learning Erlang, right? But in a way, it does. Like everything I do helps me in jobs. It helps me think. It helps exercise my brain, whatever, right? Um, so if all you ever keep in mind is like getting something done, then you just won't enjoy it. So I try to like in my stream, I have a portion where I'm just doing something for fun, like this Erlang. I do it first, and then I spend a portion working where I'm actually like doing something because I need to have results. Um, you don't have to spend a lot of time doing stuff for fun, but always like doing stuff a little bit for fun. If I'm interviewing somebody and they don't contribute to open source projects at all, they have no GitHub repository of their own that they've done anything with, I'd be like, well, okay, so why are you doing programming? It's like, oh, they don't say it, but it's like, yeah, well, sometimes they do. They say like, oh, it's just a job, whatever, I do it. That's fine. There's probably a lot of places you can work just as like it's just a job, but it's one of those things that I think requires a certain amount of like upkeep because things move so fast. So it kind of helps for it to be a hobby also. So if you start feeling like you're not enjoying coding, then do the thing that you think you would enjoy for coding. Like sometimes it's really stupid and our brain stops it before we even like allow ourselves to consider it. We're like, you know what I really like to do is like play around with this other language or try out like making this other stupid site or whatever. Like um just try out that other thing because it'll help you keep motivated. Web also is very hard because often you're dealing with frameworks and even HTML and JavaScript or TypeScript, like so much of it is dealing with something like the DOM or shadow DOM or whatever. And React is like, you don't know how it works. So it's another layer away from the machine that you're programming on. So at some point you just feel like you're remembering like just rules instead of like understanding how to program. So I always suggest like learning how, spend some time with a much, I wouldn't say lower level because functional languages are fine too, like Scheme or I don't know, whatever, right? Um, but they're basic, right? Like you're not using some complex framework on top of it. And it really lets you focus on programming instead of just learning how to use some framework. But I think a lot of people get into things for either web development or for game programming, and now you're in like Unity or Unreal, you're in some kind of like React framework with Next.js, who knows? Like, and you're kind of programming but only part of the time. So try to spend some time just programming with like a basic language that could even be TypeScript or JavaScript, but just just JavaScript, like, more like Node.js, where you're just programming low level, not even on a website, you're just like running it, just like I am here. Anyway, there is a lot to learn, but just like this book, you kind of see me tackling it. I am here so far. I don't really need to finish it before I use it. I'm pretty sure I can start using it very soon. But it's good to know what you're using. So there you go. I hope that's useful. I think most people that I've given that advice to don't really follow it. It's because of our education system and our sort of like, our capitalistic need to like be productive and make something out of it. It's also this sort of need to succeed, to be comparing to other people. You see other people that seem like they do it so easily and so well, and you're like, it's so disheartening to see that, it's harder for you. I'm definitely not the fastest person doing anything, but I can solve problems. So, there's that. All right. Well, let's hopefully that was useful. Where am I? All right. I'm doing now the key is smaller than the node's key. So let's do another insert here. And we're given a key and a value here. And now the node is no longer no longer empty. So what we have now is node, and then we have its key and value, right? Mm, what should we call this? Like, maybe we call this node key, node value. And it has smaller and greater. But we can add a when clause in here. And we basically are saying when our key is less than, let's do less than or equal to, no, it's less than because we want to replace if it's strictly equal to. There's no duplicate values in this tree. If our key is less than the node's key, then we return node, the same key value that no, we want to return the node key and the node value because this is where we're traversing. But now we want to insert ourselves into the smaller one. So key value smaller. And we return greater like we do normally. There we go. All right, syntax error, great. So does this all match? This all matches. Now I have node value. This does not close here. There we go. So the structure of a node is node. This is just a tag. It's an atom. And then this tuple. So we have our key, our value. Then this is going to be smaller. But we've inserted our key value into smaller. And then we keep the same greater. Let's try seeing if this still works. So here we recompile it. We insert it into an empty tree. That works. And now we're going to, let's make sure that A is less than B. Yeah, okay, so atoms can be compared. So now we're going to put in, we're going to make a tree here. Whoops, node. And we have an existing, it has a key value, so let's put an existing one. Like name, and the value is Frank. And then we have smaller. We'll just make it empty and empty, right? There we go. So what this should do is move it to the left, the smaller of name. So here it is. Now you can see that it made a new node under the smaller side and left the greater side the same. I could have made another like node here, I guess. It's just getting a little messy. I won't do it. It's just going to be too messy. Um, so yeah, I moved it to the smaller side, which is exactly what we wanted. See, name, node, and then here is its key value, smaller, greater, just like we said in here. Key value, smaller, greater. And smaller and greater is a node itself, so it can be node nil. All right, now we're going to have one where key is greater than node's key. Insert key value node, and we get the node key, the node value, smaller, greater. But now we have when key is greater than the node key. So now we return node, comma, the same node key, the same node value, and the same smaller, but now for our greater, we want to insert ourselves. So key value greater. Right? Okay, so this should work now. We recompile. We can insert into the left side. That worked. And now we can try to insert on the right side. That's a little dark, right? Oh, no, D is not less than GH health. Uh-oh, this is not working. Oh, the key is name. So we need something bigger than N. I don't know. I'm running out of concepts. There we go, S time. And now it's on the right because S time is greater than name. So we can recursively call this and do tree insert age. Whoops. Yeah, right. It's age 25, comma, and now this whole thing. And now you can see it's inserted. We have Frank. We have name as the key here, age on the left, S time on the right. And if we do it one more time, we can put something on the far left, like AAA, comma, 999, comma, this whole tree thing. And now we have Frank, age, but on the left of age, we have AAA. And then on the right, nothing. And then we have S time. So if we wanted something after age on the right side here, like boo, it put boo on the right side here. So we can kind of keep doing that forever. And you can see it just keeps getting nested and nested. Oh, we didn't do one where it's equal. So if I try to make the same thing here, name, we get a no function clause matching because there's none of these that match where the key is equal to. So here we say equals, insert when it's equal. And what do we do here? We're basically going to just replace the node value, right? With our value. Why doesn't it like this now? Because I removed one of the semicolons. And then now this node value we don't care about because, yeah, we don't care about this one because we're replacing it. That's the existing one in the node. So now when I compile this and I insert name twice, it's basically replacing name that was Frank to the number 1. How fun. What's left to do on this example tree implementation is creating a lookup function that will let you find a value from the tree by giving its key. Either the node is empty, so that means we couldn't find it, and one where the key is found. We return undefined if we can't find it. Otherwise, we'll return OK value. The reason for this is that if we only return value and the node contained the atom undefined, we would have no way to know if this tree, yeah. So a lot of times you see something like OK and then, the value. Or you'll see error and reason. And then you can pattern match. So there's no confusion. All right, should we try to write lookup? Let's try to think on our own and write lookup. So if the node is empty, we can actually type empty in here, right? I think. Then we'll just return error, comma, key does not exist. Now let us add this in here as lookup. And it takes 2 parameters. Lookup to undefined. Lookup key. All right, doesn't like this. I don't think it likes a function in here. There we go. All right, so I'm very incremental. Now I can do tree. Here, let's give it this long tree here. We'll just call it, now let me give the tree without the 1. Yeah, let's do this one. This tree. So we'll do test tree. So now we have this here, and now we can do lookup on this tree. tree lookup, and we pass in a key. So let's look for boo. And right now, if we pass in test tree, it'll fail because we don't have a function that takes in a non-empty list, a non-empty tree. But it means if we pass in a tree empty, we'll just get this error, right? Key does not exist. Great. And now we write lookup key. And let's say that the key is this one. So in this case, the key that we passed into lookup is the key in its node. So what do we return? Do we return just a value? I guess we return just a value, right? Okay, so let's test this. This one still says does not exist. But now if we pass in a tree that has boo and a value 10, and it has tree empty for its values. Where did I screw up? Tree empty. This should close this. This should close that. This should close that. There we go. No function matching. Oh, right, because I typed it in wrong here. It needs to start with node. Yeah? All right. There we go. So this time it found it and it said boost 10. Great. And the empty tree still works. Does not exist, right? Rewatch the VOD and your advice really helps. I'll try to keep going and find the fun in programming even if it's tough. Have a great day. And if you don't enjoy it, like it's a question you'll have to ask yourself, like why are you doing it? It's not a nice question, right? Maybe you feel like people expect you to, or it's what the major you signed up with. But God, like doing something you don't like day after day, sometimes at work when like they're asking me to do work on this project that I don't like, it's like misery day after day working on this thing you don't really enjoy. And then I find a way to kind of, switch it or change it into something that I can enjoy more. Sometimes that means like finding a way to switch teams or the project I'm working on. Sometimes it means a different way of looking at the project and finding ways to like often to complicate it but make it more fun for you. So, yeah, good luck. All right. I am now going to finish this function. So we found one that exists if it's on the top. Otherwise, the key might be smaller than the one that is in the node, right? So this is our key, and then we have a node, and we have the node key and the node value, which we don't really care about the value. And then we have smaller and greater, right? But here we're saying when our key is less than, let's say less than or equal to the node key, then we want to we return lookup the same key, but this time with smaller. This seems right to me. Yeah, and basically in this case, node value doesn't matter and greater doesn't matter. And if smaller happens to be empty, then it means the key doesn't exist, right? If our key is smaller than node key, this makes sense. So we'll just copy this and we just change this to greater. When key is greater than node key, then we call greater, right? All right, now this should be our whole function now. So let's compile again. We'll do a tree lookup here. Our old tree lookup, what is this one? Boo, yeah? Yeah, it returns the value 10. And now what do we call it? Tree value, was it? Tree something. Test tree? Yeah, there's our test tree. So we're going to do tree lookup and we're going to pass in, let's look for, the easy one is name from test tree. And name is Frank. Now we look for age. Whoops, that's not how you do it. Age 25. You see that over here. We can look for boo. And that's 1. And let's look for S time. And we got 19. So our function seems to work. Great. Let's compare, I guess. I wrote 4. They wrote 4. Nil. This is when it's equal. It's kind of the same as my function, right? Yeah, this is the same as this. Then here they have, yeah, they just turned it to underscore instead of the thing I have. Ah, interesting. They simplified it because they're like, we don't care about any of that since it's the last case. That's kind of nice, sure. Like you don't have to do this comparison. You know that it's greater than, right? Because it's exhaustive. But at the same time, it's kind of like not as clear because remember with the if statements, they like to do it exhaustively. Hey, Eric's Edge, how are you? I'm just finishing up because I got to do a work call. And then I'm going to restart the stream later, probably to work. But just finishing this. Oh, look, they gave us a tree here to play with. Let's try. Should we try this out? So this gave us the same. Yep, that gave us the same results. Mark Anderson. Oh, they're building up the tree. I don't think I copied the whole thing. Let me do this. They did T1 is equal to this. Right, so now I have T1. Now I copy T2 is equal to this. And I should have, yeah, Woodland, nil, Anderson, nil, nil. And then I can use this to insert all of this stuff into T2. And look at that. Looks beautiful, looks exactly the same thing. Now we can look up Anita Bath. And we got her email address. And we can look up Jacques Requin. Oh, oh, that's what it's supposed to say. Undefined. Whew! I was scared our thing didn't work. Um, yeah, we don't have deleting notes or rebalancing. That's fine. If you've understood everything in this chapter, thinking recursively is probably becoming more intuitive. A different aspect of recursive definitions when compared to their imperative counterparts, usually in while loops or for loops, is that instead of taking a step-by-step approach, do this, then that, then this, then you're done, our approach is much more declarative. If you get this input, do that. This otherwise. I don't even really agree with this. You're describing what things are um, more than like you're describing the answer. You're saying like when you look something up and the key is greater than your current node's key, the answer is the same as looking up with the graders. Like you're describing it. Anyway, um, oh, they made a joke. Holy shit. They put a link to the very beginning of this chapter. You get it? It's like if you're still not getting it, go back to but now you're recursing over and over until this is false, and then you go back all the way until you can continue. Joking aside, recursion coupled with pattern matching is sometimes an optimal solution to problems of writing concise algorithms that are easy to understand. So yeah, so you subdivide them and everything like that. A discussion, the author versus himself. Okay, I think I understand recursion. I get the declarative aspect of it. I get it has I get it has mathematical roots like within variables. I get that you find it easier in some cases. What else? It respects a regular pattern. Find the base cases, write them down, then every other cases should try to converge to the base cases to get your answer. It makes writing functions pretty easy. Yeah, I got that. You repeated it a bunch of times already. My loops can do the same. Yes, they can. Can't deny that. Right. A thing I don't get is why you bothered writing all these non-tail recursive versions if they're not as good as tail recursion ones. Tail recursive ones. Oh, it's simply to make things easier to grasp. Moving from regular recursion, which is prettier and easier to understand, to tail recursion, which is theoretically more efficient, sounded like a good way to show all options. Right, so they're useless except for educational purposes. I get it. Not exactly. In practice, you'll see little difference in the performance between tail recursive and normal recursive calls. The areas to take care of are in functions where they are supposed to loop infinitely, like main loops. There's also a type of function that will always generate very large stacks, be slow, and possibly crash early if you don't make them tail recursive. The best example of this is the Fibonacci function, which grows exponentially if it's not iterative or tail recursive. You should profile your code. I'll show you how to do that at a later point, I promise. See what slows it down and fix it. But loops are always iterative and make this a non-issue. Yes, but my beautiful Erlang. Well, isn't that great? All that learning because there is no while or for in Erlang. Thank you very much. I'm going back to programming my toaster in C. Not so fast. Functional programming languages have other assets. If we found some base case patterns to make our life easier than writing recursive functions, a bunch of smart people have found many more to the point where you will need to write very few recursive functions yourself. If you stay around, I'll show you how such abstractions can be built. But for this, we will need more power. Let me tell you about higher order functions. So we'll be doing that next, I guess. Yeah, I find that usually I have no issues by using like enums and stuff like that. Um, reduce and all that. So, yeah, that's our Erlang for today. I hope um I hope you can enjoy that. If you're watching this later, hopefully that makes sense. I'm going to take a break, drink some more coffee, and then continue working. I wonder if I should just like, instead of quitting the stream to do my work call, I can just like mute myself and yeah, I'll just mute myself and then put a screen up saying I'm getting coffee or something. I'll change my screen message actually because it's